Now we use this idea of a primary alcohol oxidizing to carboxylic acid to give us the alcohol test for people who've been driving. The alcohol, of course, and alcohol being primarily ethanol, reacted with an oxidizing agent, some chromium, dichromium in this case, which normally has a red to green colour, mostly red to be honest. And if the alcohol is oxidizing in any redox reaction, something must be reducing. Redox reactions always involve oxidation and reduction. So there's the oxidation to the carboxylic acid, and the reductions in the chromium, the chromium 6, the chromium 3, plus 3 ion, which has a very strong green colour compared to the original chromium. So our bodies metabolize alcohols just as we would in a laboratory, oxidizing those alcohols, taking something like ethanol, the primary component of alcohol, oxidizing it using the enzyme dehydrogenase, oxidizing it into an aldehyde, acetaldehyde. Now, acetaldehyde is toxic to our bodies, and so a second enzyme, aldehyde dehydrogenase, aldehyde dehydrogenase, oxidizes the aldehyde that's been produced, that acetaldehyde, oxidizes it into acetic acid. So a two-step process for your body to oxidize alcohol eventually into acetic acid. Using the dehydrogenase enzyme and then using the aldehyde dehydrogenase enzyme. Now, if you're consuming the alcohol too fast, then your body struggles to oxidize the alcohol completely in a rapid fashion. So sometimes a lot of that acetaldehyde hangs around in the body, not being oxidized. And as that acetaldehyde builds up in the body, that's what's primarily responsible for that sort of hangover feeling people get if they've taken too much alcohol too quickly. It's all about the body not being able to keep up with your consumption and oxidize it fully through to the acetic acid quickly enough. And that gives those symptoms. Now we use compounds like antabuse in medicine to actually try and prevent that oxidation of the acetaldehyde in the body. So that we actually purposely make people feel sick and poorly, to try and wean them off alcohol, to try and generate a body reaction where you eventually don't like taking alcohol. You get enough hangovers and get bad enough hangovers by inhibiting that oxidation, you get to a point where you just smell alcohol and you just start feeling ill automatically. Now, some people, probably by illegal means, try and substitute methanol for ethanol in their alcohol drinking habits. Methanol is often cheap, gives the same effects as alcohol, but the oxidation products produced from aldehyde and formic acid, they are way, way more toxic. It can lead to blindness and perhaps death if too much is consumed. Not a good idea to switch ethanol for methanol. Still people do it. Oxidation products from the methanol are much more toxic to the body. Now, to cure the patient who's had methanol poisoning, the solution for the patient is actually to give them alcohol. It sounds kind of crazy, but it works. Your body and the enzymes in your body would much rather, more readily, oxidize ethanol than methanol. So if you give the patient alcohol, the enzymes, the dehydrogenase enzyme and the aldehyde dehydrogenase enzymes, you'd much rather work on the ethanol. So the methanol is left unoxidized, and will eventually pass out in the body normally through your urine. So you can avoid that buildup of those toxic substances, the formaldehyde and formic acid, by giving the patient ethanol to oxidize instead. Sounds kind of weird, like it shouldn't really work. But it does. Now, ethylene glycol is a substance which is sometimes used by less scrupulous people, and they're trying to deliberately kill people off. Ethylene glycol, which is also used one of the main ingredients in antifreeze. Yeah. Even more toxic than methanol is this ethylene glycol, this dye alcohol, producing glyoxal and oxalic acid. So the ethylene glycol oxidizing those two groups, so we turn them into aldehyde groups. And the second step, glyoxal. Oxidized a second time, this time with the aldehyde dehydrogenase enzyme, oxidized through into the comparative carboxylic acid. Again, increasing the amount of oxygen in the molecule. So the alcohol is also can react as an acid or a base from a Chem 141 chemistry. You should remember that an acid is a compound which can donate protons. Acids donate protons. Bases pick up protons. That's our 141 Bronsted-Lowry definition. So we see the simple alcohols reacting with water in an acid-base reaction. Water, of course, able to act as either an acid or a base in that proton transfer. At general level, that's what our acid-base reactions are. Transfer of a proton from the acid to the base. So that oxygen to hydrogen bond breaks, it gives off proton, and the electrons go to the oxygen. So we produce this oxide ion, protonate the water to produce hydronium ions. Our alcohol is acting like an acid. We can also get the alcohol to act like a base. This is page 81. Get the alcohol to act like a base by picking up a proton. Using one of the lone pairs of electrons on the oxygen, taking a proton from hydronium ions to produce this positively charged species, this oxonium ion, in water. So the alcohols can do either job. We can sometimes use this chemistry of alcohols to extract organics in a chemical reaction. There are lots of reactions where the phenol might be the compound that we're interested in, trying to recover in the reaction. And there might be a lot of dirt, a lot of other compounds mixed into that organic layer. And so we can use that acid-base chemistry of the alcohol to separate it from other organics which are in our solvent. So using our aqueous solution of sodium hydroxide, the organic of course being dissolved in something like dichloroethane or maybe diethyl a solvent, they won't mix with water. If we shake them around at that meeting of the two layers, we can get a chemical reaction to occur, an acid-base reaction. Put in some base, the alcohol reacts as an acid, giving off its proton, becoming this oxonium ion, which then attracts the sodium. So we get this sodium phenoxide molecule formed. Because it's ionic, it's no longer soluble in the organic. So it moves into the aqueous layer. Our organic, reacting as an acid to produce this ionic compound, and the product is no longer soluble in organics, it's soluble in water. So with those two layers, the target chemical you're interested in will actually move to the water layer. While trapped in the water layer, we can separate it from the organic, where all the other dirt and impurity is, separate it from that organic, and then react it with hydrochloric acid. The conjugate of an acid, the conjugate is a base. It's good at picking up protons to reform the original compound. So we're using both its acid and base properties. And when it picks up a proton again to reform the phenol, this substance is no longer soluble in water. We've flipped its properties once more. So we can add in some fresh organic solvent, which doesn't have any impurities, and re-extract to get pure organic product.